Let us talk about this problem. We are given an array of integers. In this array, all numbers appear even number of times except one number that appears odd number of times. And we need to find out that number. For example, if you take a look at this example, see 4 is a number that appears even number of times. How many times it appears? It appears 4 times. 1, 2nd, 3rd, 4th. 5 is another number that appears even number of times, 2 times. But 3 is a number that appears odd number of times. That's why our output is 3. If you take a look at this example, here we have 7 appearing 2 times. So it's an even appearing number. And 8 is the only number that appears 3 times or odd times. So our output is 8. Suppose there were more numbers like 5, then 5 must appear or even number of times, because there can be only one number that appears odd number of times, and we can make this assumption. We can assume that our always input array contains numbers in such a way that there is always going to be only one number that appears odd number of times, and our task is to find out that number. Please pause this video and try to think of an approach for solving this problem. Let us first talk about a naive solution to solve the problem. The idea of naive solution is traverse through the array. For every element, count the occurrences of it, right? So we traverse through the array this way. We have a function find odd that takes the array and size of the array as input, right? For example, this array, this is going to be our array and size of this array is 5. So we are going to pass this array and size of this array is 5. Now we run through the loop. For every element, we initialize the count as 0. Then we run another loop to count how many times the current element appears. So for I equal to 0, we are going to run a loop for j equal to 0 to end, right? And we are going to increment the count when array I and array j become same, right? So for I equal to 0, we have 7, array I is this. We will begin from here, count will become 1, then remains 1, 2, 3, 4. So count is 4, it's not odd, so we do not come inside this if condition. Now when we come to I equal to 3, count, we begin from here, count remains 0, becomes 1, remains 1, remains 1, remains 1. So count is 1, and we come here inside this if condition and we return this number, right? And this number is 3. Suppose this 3 was at the end. In that case, we would have run this loop till end, right? And that's why the worst case time complexity of the solution becomes big O of n square. Please note that there exists a better solution based on hashing that requires big O of n time and big O of n auxiliary space. But in this video, we are going to talk about an interesting bitwise operator solution which is going to work in big O of n time, or you can say theta n time, and big O of 1 auxiliary space. So this bitwise operator based solution is going to be even better than hashing. That's the best solution for this. So please pause this video and think for a moment, how will you use bitwise operators to find out the answer as 3? The idea for efficient solution is to use bitwise XOR operator. Here are some interesting properties of bitwise XOR operator that make it useful for such questions. Bitwise XOR of x, where x is any number, with 0 is going to give you x. See what happens in bitwise XOR. We do consider binary representation and we do bitwise XOR bit by bit. And bitwise XOR works this way: if 2 bits are different, then only the output is 1, otherwise 0. So in case of 0, what is going to happen? When you have 0 in the binary representation of x, you are going to get 0. When you have 1, you are going to get 1, because 0's binary representation is going to have all zeros, right? That's why XOR of 0 with x is x. Now XOR of y is same as y XOR x. It's commutative, right? You can change the order because it's just binary representation and then bit by bit XOR operator, and do 2 bits different than 1. So order doesn't matter whether first one is 1 or the second one is 0. It's also associative, right? You have x XOR y XOR z equivalent to x XOR y XOR z. Now one more interesting property, XOR of x with itself is going to give you 0. See, binary representation of x and x, they are going to same, and whenever you have same bits you get 0. So you're definitely going to get 0. From this property and this property, I can say if I do XOR of a number x with itself odd times, right? Or I say that number of appearances of x is odd, then we get the result as x. For example, 4 XOR 4 is going to be 4, right? Why? Because these two XOR is going to be 0, 0 XOR 4 is going to be 4, right? From the properties. Now similarly, if you do 5 XOR 5 XOR 5 4 times, even number of times, if you do XOR, what is going to happen? If you have even occurrences of the number, then what is going to happen? You are going to get 0, because these two will cancel out each other. 0, these two will cancel out each other. You will have 0 cross 0 XOR 0, and 0 XOR 0 is going to be 0, right? So if you consider even occurrences of a number, and if you do bitwise XOR, you are going to get output as 0. And if you consider odd occurrences, then you are going to get the output as the number. Now you have idea, you know we are going to use bitwise XOR operator, you know these properties. Please pause this video and try to think of an efficient solution yourself. The idea for efficient solution is to simply do XOR of all the numbers and you get the result. As simple as that. We initialize the result as AR or 0, then we run a loop from second element to last element, and we simply XOR every element with the result. Now how does the solution work? It's basically based on the XOR properties that we talked about. If you take a look at this example, right, where we have 4 appearing 3 times, it's the odd occurring number, and then we have 7 appearing 4 times and 8 appearing 2 times. All the other number appears 2 times, and 4 is the only number that appears odd times. So if I compute XOR of all these numbers, what is going to happen? I can rewrite this expression as this. I put all the 4s together because of the commutative and associative properties. I can put all the 7s together and I can put all the 8s together. And 4 is odd times, so it's going to give you result as 4, as we discussed earlier. 7 is even times, it's going to give you result as 0. 8 is even times, it's going to give you result as 0. So if you have even more even appearing numbers, they are all going to give you 0, 0, 0, right? So you will have only 4 and then some zeros, right? The odd number and some zeros. And then see, if you put these 7s first, then again 0, 4. So commutative associative property, we can write always the odd appearing number first or at the end, doesn't matter. Now all these 0 XORs, when you do XOR of 0 with itself, you are always going to get 0, whether 0 is odd times or even times. In case of even times, you anyways get 0 for every number. In case of odd times, you get the result as x itself, but x is 0, so you will get 0. So you will get 0, doesn't matter how many times 0 you have. So 4 XOR 0, x XOR x 0 is x only. So we get the output as 4, right? So it's the only odd appearing number that you will always get output of this program function, right? Now, what is the time complexity of it? It's clearly theta n. We are running a loop n times, right? And auxiliary space, it's clearly big O of 1. We are not using any auxiliary array or anything. So this is really an interesting bitwise operator based solution to solve an array problem.